Hi, I'm Matt Needham, and this is my lecture on combustion air. What is combustion air? It's all of the air that a heating appliance needs to operate safely and properly. It's the air that needs to come in and mix with the fuel, let's say natural gas, to have proper combustion, extra air to move things along, and lower the humidity of the products of combustion so it can't condense in the flue pipe. It's also the air around the furnace for safety so it doesn't get too hot around the air. You have enough space around it so that if you're working around it, you're in a safe condition. So it's all the air that a furnace needs, okay? Or a heating appliance of any kind. And the chapter from the mechanical code is more dedicated and really a lot about natural draft combustion. Now, natural draft combustion means that it's just allowing the natural airflow to come into the heating appliance and mix with the natural gas and create ignition, and then those warm gases to rise up in like a negative pressure and go out a chimney pipe, somewhat like if you had a fireplace, the warm combustion gases, the smoke essentially would go up the flue pipe, up the chimney pipe. And a lot of this chapter is about that, and so I'm going to go over some different ones and concepts and try and get you updated about some of the newer equipment. So first here, one appliance though that still is absolutely designed this way with natural combustion air is a hot water heater, where you have the hot water heater and then you have the fire down here, and the cold pipe comes in and the hot pipe comes out, and then the products of combustion come out the flue pipe, and then you have this thing here that looks like this that sits on top where there's a little air gap, and then the vent pipe goes up and either out of the building or out of the over the top of the roof or whatever, and that's your vent pipe. And then air can get in here, and air is also, there's going to be a place here where you can definitely suck in fresh air to also come with, you'll have a natural gas pipe, let's say, bringing natural gas in to mix with the air that just naturally gets sucked in to the firebox there. So this relies on natural ventilation. Now the draft hood, once you get heat going up there, and a lot of times it may take a good 45 seconds or so, the warm products of combustion are lighter and they rise up, and it draws extra air in this way, and moves the products of combustion along. Now, one of the main byproducts of combustion is water vapor. When you burn natural gas and oxygen, you mix those together, you get water vapor. But then as you go up the chimney pipe, it's cooler. And if it's not moving up at a very good rate, it can hit the cooler chimney pipe and condense back into a liquid. And that's actually fairly acidic water that it makes. So to help it move along and not condense, and sometimes you may hear in an old hot water heater like tss, tss, or a furnace tss, tss. When it first starts up and gets going, you may have a little bit of that condensation where water droplets are dropping out of the flue pipe, the chimney pipe, back down, and you could hear it sizzling. We don't deal too much anymore with natural ventilation type furnaces. The one that you probably might run into quite a bit would be maybe like a wall furnace that just is sitting mounted right into a wall, and the flame is down lower, and you have a vent pipe going up the top. Yes, that might be natural ventilation. But for heating, as far as furnaces go, we pretty much are always using power venters or combustion blowers. And I'll get into that in a minute. Here, let me go over a few more points on the first page. It says here, the burning of fuel inside an appliance heats the air, causing it to rise within the appliance along with the products of combustion and exit through the flue outlet. As the hot flue gases exits the flue outlet and enters the vent through the draft hood, a Venturi effect is created, drawing cool, almost stagnant air from the compartment to mix with the faster moving hot flue gases. And you're getting this sort of thermosiphon action where the cooler air is being drawn in below and then rising up out the chimney pipe. And you always have to, here's another general principle, period, for combustion air, is you always have to have a source of air, essentially fresh air that can go and feed that. You can't starve your appliance. You have to have the right mixture of air and natural gas, and we're going to get into that in a minute, to have proper combustion. Okay, and also this idea of the one or two openings, let me just kind of give you that concept a little bit. A lot of times you'll find all over the place in an attic, you'll see these vents at the bottom of the attic with screens on them. And if you walk around the outside of a house, you'll see that. And those should not be blocked with insulation. Sometimes companies come and do blown-in insulation and block those. That shouldn't be. They should rake that out and tamp that down. And then at the top of the house, you'll have the gable vents off of your triangle at the end where you have these louvers. And so you actually naturally have the air flowing into the bottom of the attic, rising up, and then going out your gable vents. Or some people have whirly-bird spinners on top to ventilate. That helps. And that keeps a nice flow of air going through there, which keeps your attic a little bit cooler in the summer particularly. And also if you're working in there, you have this natural flow of the air coming in and heating up and going out, which provides better air for you if you're working in there. And we have this concept over and over again where air comes in down low, warms up, and goes out. Even that's how we have actually natural infiltration, air leaking into a building generally, warming up, and exfiltration going out. So we're always trying to have a good sufficient supply of air for combustion air, but also for people and technicians working also. You'll also see, like, for a furnace that's in a closet, when you open that door, it's like usually an upflow type furnace where the air comes in the bottom. You'll see you'll see a vent going to the attic, a vent, and then you'll see like this duct that looks like it's just stuck at the bottom, near the bottom of the furnace that doesn't have anything on it. And you're like, what the heck is that? Well, that is those two vents, the air down low, naturally, even when the furnace isn't running, it's going to rise up and go out through the top into your attic. And you'll have natural flow through there. And even if you had a tiny natural gas leak, that's going to help keep that closet ventilated. And it's going to keep more fresh air available to the furnace. Because a lot of times an older furnace like that, it's relying on those two vents to provide the air that needs to mix. And you need way more air than you need natural gas to create proper combustion. So it's relying on those two openings to allow a good path of airflow. Okay? All right. Let's get on with this furnace. This is, they show you in the chapter this picture that I drew of kind of a natural draft type of furnace that doesn't have a power venter or a combustion blower, where it's just relying on the natural warming of byproducts of combustion to go out the flue or chimney pipe. So here you've got 1 cubic foot of natural gas, and in order for this to work right, you need to mix it with 10 cubic feet of air for combustion. Now, air is made up of about 80% nitrogen and 20% oxygen, approximately. There's actually 1% of other gases in there like argon, but we're not going to consider that. So if you think of that, here you would have 2 cubic feet of oxygen mixed with 1 cubic foot of natural gas burning purely, right? And even when you go to light a torch, you have pure oxygen mixing with acetylene. So it's the oxygen and the natural gas. And you can see that you need twice as much oxygen as natural gas for proper combustion. We're also getting 4 extra cubic feet of air, excess air to help move things along and just to make sure we have plenty of it. And then you have a fire in here, and then you have an opening in the front of your furnace, and these are usually older furnaces, where you'll have 15 cubic foot of dilution air, like the air that came in here from our vent pipe. You'll have that dilution air, okay? Also, and so then that helps move along the products of combustion. It causes the relative humidity to be lower here, so that you're not as likely to have water condensing onto your vent pipe or down below, and then goes out. And whatever you put in, you get out. So here you've got 1 plus 10 is 11, plus 4 is 15, plus 15 gives you 30 cubic feet of products of combustion coming out the chimney pipe, okay? Let me also talk for a minute. I didn't mention the point. Another reason for the draft hood and this kind of design for these natural draft type of heating appliances is to prevent downdrafts. So wind is a weird thing, and if you were to get kind of a wind going down here, when you're just down to your pilot light, baby pilot light standing there, the wind can get down and blow that out, but the fact that you have this opening allows the air pressure to diffuse itself and come out here and not blow straight down to the bottom of your hot water heater. The same thing is here. Okay? All right. Let's move on. Now, another general concept, especially when you have natural ventilation, or even when you have furnaces with a power venter or a combustion blower. So the majority of furnaces out there are like this, but they have a fan. So we'll change the diagram a little bit here. It'll be easier for you to see. So, you know, this is going to be coming off the top here, more like this, right? You can have a bit of an angle here. That's okay. Coming there like that. And then you're going to have in here a fan, a power venter or combustion blower that's sucking the air and the natural gas in and then power venting it, blowing it out. And most of the furnaces out there are this way, okay? And it's not natural draft, and so, but you still need to have a source of air, fresh air. And so in the book there's a lot of math, but things are changing, and I decided, I used to do like, I was going to write all these formulas on the board, and I thought, no, things are changing, and you'll see why, because the chapter is more dedicated to this old stuff, why I'm not going to do the math for you. But the idea is that you have to have enough air, right? And the idea is if a small appliance, like if this guy was in a big kitchen, there's enough air from the kitchen and air that leaks into the kitchen and flows in and out of the kitchen where you don't have to absolutely have a vent from the outside providing air, okay? Garages is another place where you'll see a lot of heating appliances, hot water heaters, furnaces, right? Also, you'll notice in garages, you tend to have that upper and lower opening concept, where you'll see these screens down at the bottom of the garage, these little openings about this big, about maybe 8 of them in a garage with screens, and then you look up top near the top, and you have another one. And that's so that your garage can stay ventilated, that the air comes in, warms up, and then goes out those vents. Because people start up cars, they'd work on projects, they spill gasoline, they have paint. Also, if you have a furnace or you have a hot water heater, you can't have the garage totally sealed up and then run it, because it's drawing its air, if it's in the garage, from the garage, so it needs to have a source for that air to come in. Okay? So I'm trying to get you more on the concept, because there's a lot of changes going on right now in our industry. Okay, so you have these furnaces, and these are like 82% efficient furnaces. The natural draft ones are more like 70%, where if you had a big natural draft furnace that you have 100,000 BTUs quality of natural gas, the amount of heat that you're getting out the pipe, into the plenum of heat that you're trying to get for you, might only be 70,000. But now with the power venter and more modern technology, 82, 83% efficient, where if you're using 100,000 BTUs quality of natural gas into your pipe coming out here, into your ductwork, you're getting more like 82 or 83,000 BTUs, okay? With this combustion blower, power venter, and more modern type designs. But the big point, I just want to get the concept, is that you always have to have a source of air. Whether it's a heating appliance that's in a big room and there's enough infiltration, exfiltration, there's a lot of math in this chapter about calculating that. And I'll show you one reason why I'm not going to go over it, because of a new law that was passed in 2019. What we have going on. It kind of makes this, and going forward, going to be somewhat outdated. Okay? And even just a point on hot water heaters, they've tried to make them more and more efficient, and they're called low NOx, low emissions. They're more efficient. They use more fuel. They use less fuel. They heat the water very quickly. My personal experience with that, and they started coming out with these little different designs maybe 7-8 years ago, is that they're good, but they're a little more fragile. I don't think they last as long. I put one in like 6 years ago, and I just had to replace it with a much more even high efficiency modern one, which was quite a bit expensive. And they make them very difficult to work on with all these sealed chambers in there for efficiency. So anyways, enough about that. And then with these furnaces, again, about 82% efficient. All right. Now, makeup air. What is makeup air? Air that is, let's say you have a furnace or a hot water heater that's, or even a dryer that uses air for combustion that's in the house, right? Or in a commercial building or whatever. If you don't have proper ventilation, windows that can open, or enough infiltration, you have to provide the makeup air, or you need the makeup air anyways, whether it's through natural means by opening a window or infiltration, or having an actual fan that's bringing air in so that you have enough air for your heating appliances, okay? We have exhaust air, or air that's exhausted out the top of these heating appliances and even dryers. And then we have to provide makeup air to make that air up that's leaving, that's creating that negative pressure in, let's say, the building. Okay? Okay. Let's move on here. And again, with the openings, 1 and 2 openings concept, they need to be within like 12 inches of the ceiling and 12 inches of the floor, not directly, and up off the ground so things can't build up and block that. And that's what you see like in a garage, right? In that when you have these air vents, one's near the floor within 12 inches, the other one's near the top of the garage. Let's talk now about these more modern furnaces. They've been around a long time, but here we have a more modern furnace. Now, in the state of California, very green state, very concerned about the environment, global warming, cutting down on emissions, not using as much electricity, not burning as much natural gas, a lot to do with global warming and saving energy and pollution. As of last year, 2019, any new furnace that's put in has to be one of these high efficiency furnaces that is not relying on the air around it to be used to mix with the natural gas. So then all those calculations that are in the chapter, certainly none of that would apply to one of these new furnaces if you go to install one of them. Let me explain how they work, why they're so efficient, and a few other details about them. They've been around a while, but they've gotten better and better and more efficient. Now they're kind of mandated by law. And it's this, that you've got, yes, a vent or chimney pipe that goes out the top to get rid of products of combustion. That hasn't changed. You have this blue natural gas pipe that's got to bring in natural gas to burn. But then you have another pipe that this is this intake pipe that has to bring the air from the outside in. And then all of this inside, the power venter, the gas valve, the heat exchanger where you see the blue flame, this is all kind of sealed up, kind of hard to work on. And it's like a sealed chamber. And so that the air that comes in goes out, and we're not relying at all on the air around it. And you'll even notice that with these type of furnaces, you'll see a lot of vents like sitting on top, little air vents on top, on the bottom, and you'll see people piling things up, blocking the air vents. They're not even giving people the chance to do that. By the way, when you do that, what happens to a furnace that doesn't have enough air is the flame goes from blue to orange. And when you see an orange flame, you have carbon monoxide. When you have perfect combustion, which is really, really, really difficult to attain, which can be proved by testing, it's possible, a beautiful, perfect blue flame, but then you'd have to prove it. Perfect combustion, which is about, a perfect mixture of oxygen, air necessarily, and natural gas, like 10% natural gas, 90% air, produces no carbon monoxide. None, okay? So, anyways, with that, if you start starving any heating appliance, the flame turns yellow, you get a lot of blackening of everything, you produce carbon monoxide, which is poisonous, etc. Back to our high efficiency furnace now, and concept is you've got the air that comes in, and then the natural gas mixes and heats up, makes a fire and then heats up a heat exchanger. But then, so the reason that it's high efficiency is this, that again, let's stick with a furnace where you're giving it 100,000 BTUs of perfect, nice quality natural gas. The amount of heat you get out of this is like 95,000 BTUs, 95% efficient. And to kind of explain that is if you were to touch this pipe or this pipe over here, it's hot, right? You're losing a lot of heat that you paid for out the chimney pipe, okay? Here they're like, let's use that heat. Let's use that heat. Let's not dump that heat outside. How can we do that? We can really have a fan that pulls everything through, and then we create this extra, you see the little orange after the red? An extra little section of a heat exchanger to really get all the heat out of the natural gas and the air that we've mixed together and burned. And when you do that, remember I told you that one of the main byproducts of combustion is water vapor? When you cool it down, you start getting water condensation. And so you have to have not only an extra pipe coming in to feed air, you also need like a PVC pipe, condensate line, draining water, because you're going to produce water out of this furnace when you're running it in the heating mode, because you're condensing the water vapor, making use of that heat, trying to get all the heat out of this, and this is barely warm at all up here, okay? That's what makes it efficient, okay? And then, you provide the heat out there. These furnaces are more expensive, and then you also have to install this extra pipe going outside and drain properly, like in a mixture of sand and I forget what it is, clay or whatever, and or gravel, and it goes outside and is somewhat acidic. I have a fantasy about planting hydrangeas there, which need acid to change the beautiful colors of the flowers. And because this water is slightly acidic, we drip it into my flower bed and we get a synergy of HVAC and botany. That's another story. Anyways, we come up here and we're dumping the heat in, and again, we still have a vent pipe coming in, but that's what makes it more efficient, is a sealed up chamber. We're bringing in the air, we're getting rid of the condensate. And by law now, and actually because it's more expensive to install and all of that, here in 2000, at the end of, I'm making this here at the end of the second half of 2020, COVID, these are more expensive to buy and install, Also because you have to run these extra pipes, you know. So some people are actually going with heat pumps as an alternative, and we'll see how all that plays out in the future. Okay, let's move on. Okay. Now, if you are providing air for any space, right, you have to have a certain amount of openings, okay? And what they're saying is that, you know, for a garage or whatever, or anywhere that you say, well, we have fresh air coming in here, and I'm just going to have a little tiny slit. No, it has, whatever opening you have has to be at least 3 inches so that nothing can block that, okay? You can't just have a tiny crack that goes the whole distance of a building or something. It's got to be at least 3 inches so that you can actually have like a vent, okay? Also, in cold climates, it says here, it is not desirable to have combustion air openings to the outdoors. Well, therefore, every attempt is made to utilize the interior of the building as a source of combustion air. I've actually studied this. It's kind of interesting. And it kind of makes sense. I mean, just on a very basic level, the temperature of the air that you mix with the natural gas affects the fire, in that you don't have as good a combustion with 40-degree air as you would with 65-degree air. Okay, does that kind of make sense? Which is true. And you'll see a lot of piping run through attics and things like that to kind of preheat it, and etc. We don't have much of a problem with this, though, like in where I'm from, Southern California, because, I mean, it would freaking make the news if it ever got to 32 degrees here. It would be like a big story, okay? So, all right. On Louvers and Grills, if you are taking air from the outside and you have louvers and grills, which makes sense, a lot of times you'll have louvers or grills so that you're bringing air in, but like rain can't get in or water, right? And so if you have, and you're calculating the area that you need for fresh air, is assumed that wood louvers have 25% free area and metal louvers have 75% free area. What does that mean? Well, if you had something that was 10 by 10, like this, that's about 10 by 10, and then you had these louvers that came down like that, okay? If they're very thick wood, and this is 10 by 10, you could say we have 100 square inches, but because the wood is so thick on the louvers, you can only count this as 25 square inches. However, if it's very like thin metal louvers, then you could say, well, no, it's 75 square inches. So that's what they mean about the free area, is that you can't just say, well, I have an opening, but yeah, you have these louvers like this blocking a lot of that area. Okay, and I think that question shows up on a quiz that I give. All right. Okay, here it talks about ducts shall not be screened where terminating in an attic space. Why? Ducts shall not be screened. This is to prevent the possibility of obstruction of the duct when insulation is blown in the attic, a popular method for insulating a building. If no screens are installed, the blown-in insulation would simply fall in the compartment and alert the observer. Okay, so what we're talking about is that a lot of times for furnaces like this, coming from the attic, again, in the closet, you know, you're going to have probably a screen vent up here going from the attic that can bring air into your closet. But then you also have a duct that you'll see like this that comes down, and it just sticks out like this. Like that. And it always looks weird. You're like, there's this duct that goes nowhere. It's just open. It's just, what is this? That, again, that's so that the cool air can come and flow through, and that you have a nice flow of air in your closet or in your enclosed space, right? But this is the attic of your house up here. And so they're saying you can't put a screen here because if the guys come in and blow insulation in, it'll plug that up. But if you don't have a screen and this duct is just sticking up, then the insulation would fall out here and someone would say, hey, wait a minute, we have a problem, right? Also, if you have a screen up here, they'll just plug up this screen big time and you'll never know it, and then you could be starving your furnace of air. Okay, and again, you have these vents and screens like all over your attic, around the outside of your house. If you ever get insulation blown in, before they leave, you walk the perimeter of the building and make sure that those vents aren't blocked in your attic, and have them take a rake and tamp it down or whatever, move that around a little bit, okay? Okay. And you cannot have manually operated dampers where somebody can just close off one of these vent pipes, okay? You can't have anything like that. No manually operated dampers, okay? All right. Well, that concludes my combustion air lecture. Again, combustion air is all the air that a heating appliance needs around it for ventilation, to mix with the natural gas to have complete combustion, etc. Thank you.